Just 2 hours ago, data from the James Webb Space Telescope hit the servers at the Space Telescope Science Institute, confirming something no one expected. One of the objects now diving toward the sun is carrying a chemical signature that doesn't match any comet in our database. That matters because it means we might be watching an interstellar visitor, revealing its secrets in real time, and the clock is ticking before it vanishes into the solar glare. Right now, three separate comets and one candidate interstellar object are converging on the inner solar system in the same 2-week window. That's unusual but not impossible. What changed overnight is that Webb turned its infrared eye on the brightest of the group and measured the gases boiling off its nucleus. The ratios don't fit. They're close, but they're off in a way that points to formation conditions colder and more carbon-rich than anything born in our neighborhood. We're going to walk through exactly what's confirmed, what the instruments actually measured, and what remains educated guesswork. Every claim you hear today is anchored in public data from the Minor Planet Center, JPL's small body database, the Space Telescope Science Institute, and coordinated observations from SOHO, Stereo, Solar Orbiter, and a network of professional observatories across 4 continents. Let's start with the hard facts. The object in question is the one currently cataloged as the Atlas Interstellar Candidate, preliminarily designated in some tracking logs as 3I/Atlas-AUS pending final orbit confirmation. It was discovered on April 8th by the Atlas Survey Telescope in Hawaii during a routine near-Earth object sweep. Initial astrometry suggested an eccentricity hovering right around 1.02, which puts it in that narrow uncertain zone between a very stretched ellipse and a true hyperbola. If the eccentricity holds above 1, the object is unbound and came from interstellar space. If it drops slightly below 1 with more observations, it's an extreme long-period comet and still ours. As of this morning, JPL's solution lists eccentricity at 1.018 plus or minus 0.003. That error bar spans both possibilities. The object reached perihelion, its closest approach to the sun, at 0.29 astronomical units yesterday at 1400 universal time. That's just inside the orbit of Mercury. It brightened rapidly over the past week, climbing from magnitude 12 to magnitude 6.2, which makes it barely visible to the naked eye under dark skies and easy and binoculars. What made it a priority target for Webb was that brightness surge. It outpaced the standard sublimation models for water ice by about 40%. And the tail showed a distinct blue-green tint in images from amateur observers in Australia and South Africa, hinting at diatomic carbon and possibly cyanogen. Those are common in comets, but the intensity was high. Webb observed the object for 6 hours starting April 10th at 0300 UTC using the near-infrared spectrograph, or NIR spec, in its high-resolution mode. The data were processed yesterday and released to the team early this morning. According to the publicly posted observation log, the spectrum clearly shows emission lines from water, carbon monoxide, carbon dioxide, methane, and ammonia. All of those appear in normal comets. What stands out is the ratio. Carbon monoxide is running at nearly 8 times the abundance of water by molecule count. In a typical Jupiter family comet, you see carbon monoxide at maybe 5 to 15% of water. In long-period comets from the Oort cloud, it can reach 50 or even 80%. 8-to-1 flips the script entirely. The other standout is methane. It's present at roughly twice the level seen in any previously measured comet, and the ammonia line is strong, which fits with formation in a very cold environment where nitrogen ices could condense. What the data suggests is that this object formed in a molecular cloud or a protoplanetary disk much colder than the region where our own comets assembled. The leading natural explanation is that it condensed in the outer reaches of another star system, perhaps around a low-mass M dwarf where the snow line sits much closer in and carbon chemistry dominates, or in a dense patch of the interstellar medium itself where temperatures hover just a few degrees above absolute zero. If that's the case, this is only the 3rd confirmed interstellar object ever detected, following when Oumuamua in 2017 and Otan Borisov in 2019. What we don't know yet is whether the orbit will tighten enough with additional tracking to reclassify it as solar system native, which would mean the chemistry alone is the anomaly. Now let's talk about the wider context because this object is not arriving alone. C/2025 R2, discovered by the Solar and Heliospheric Observatory SWAN instrument on March 2nd, reached perihelion at zero point 0.1 when astronomical units 3 days ago and survived. It's currently magnitude 4.1 and climbing back out, visible low in the western evening sky for observers in the northern hemisphere. C/2025 K1, found by Atlas in late January, swings through perihelion at zero point 0.4 astronomical units on April 16th, and 240P/NEAT, a known short-period comet, makes its closest approach at 1.1 astronomical units on April 21st. Add the interstellar candidate, and you have 4 objects all passing the Sun within a 16-day span. Statistically, that clustering happens by chance roughly once every 4 to 7 years. So it's rare but not alarming. The orbits come from completely different directions. R2 SWAN came in from nearly perpendicular to the ecliptic. The Atlas candidate is inclined about 63 degrees, and K1 is closer to the plane. There's no gravitational link and no shared origin. What makes this moment significant is that it's happening during solar maximum. The Sun's magnetic field is tangled and active. Coronal mass ejections are launching every few days. The Parker Solar Probe and Solar Orbiter are both inside the orbit of Venus right now, taking measurements of the solar wind and the magnetic field structure near the Sun. When a comet dives through that environment, its tail becomes a natural probe. The solar wind drapes around the coma, the cloud of gas and dust, and stretches the ions into a tail that can extend millions of kilometers. By watching how that tail kinks, disconnects, or brightens, scientists can map structures in the wind that are otherwise invisible. The Atlas candidate passed through a particularly active region yesterday. Stereo ahead captured images showing the tail whipping sideways in what looks like a magnetic sector boundary crossing. That's expected. What wasn't expected is a brief brightening spike about 4 hours after perihelion that added half a magnitude in under 20 minutes, then faded back. SOHO's LASCO C3 coronagraph recorded it. The spike is real, so let's file the anomalies and go through them one by one. First, the chemical composition. What's confirmed is that Webb measured carbon monoxide at 8 times water and methane at double the typical comet abundance. The likely explanation is formation in a colder, carbon-rich environment, either interstellar or in the outer disk of another star. What some researchers speculate is that if the eccentricity stays hyperbolic and the chemistry holds, we're looking at a pristine sample of the molecular cloud that existed before our solar system formed, flash frozen for billions of years and now outgassing in our backyard. That would let us test cloud chemistry models directly. The alternative, if the orbit circularizes, is that our own Oort cloud has a population we've never sampled, objects that form farther out than Pluto in conditions we didn't think existed here. Either answer reshapes formation theory. Second anomaly, the brightness spike. What's confirmed is that SOHO LASCO C3 recorded a half-magnitude jump in under 20 minutes, centered about 4 hours post-perihelion. The likely explanation is a fragmentation event. The nucleus is small, probably a few hundred meters, and the tidal stress near the Sun plus thermal shock can crack it. When a fresh surface or a buried volatile pocket suddenly exposes the sunlight, you get a flare. We've seen it in dozens of sun-grazing comets. What some speculate is that the timing, right at a magnetic sector boundary, suggests an interaction between the comet's ionized coma and a compressed pulse of solar wind. If charged dust grains got accelerated and fluoresced, that could add light without fragmentation. It's a long shot, but Solar Orbiter's magnetometer data might show a correlation when the teams compare timestamps. Third, the orbital uncertainty. What's confirmed is that the current JPL solution gives eccentricity at 1.018 with an error bar of plus or minus 0.003. With only 12 days of astrometry, that's expected. The likely outcome is that another week of observations will shrink the error and pin it down. If it drops below 1, it's a very long period comet, period a few thousand years, and it belongs to us. What we don't know yet is whether there's any non-gravitational acceleration. Comets jet gas asymmetrically, and that rocket effect tweaks the orbit. Preliminary residuals, the difference between predicted and observed positions, are small but slightly larger than measurement noise. If there's jetting, it complicates the solution. Some orbital dynamicists are running Monte Carlo simulations to see if a plausible jetting model can flip the eccentricity either way. Results aren't published yet. Fourth, the coincidence of timing. What's confirmed is 4 objects, 3 definite comets plus 1 candidate interstellar, all reaching perihelion in 16 days. The statistical rate for such clustering is once every 4 to 7 years, assuming random arrivals. The likely explanation is pure chance. Comets don't talk to each other. Their orbits were set millions of years ago by gravitational kicks in the Oort cloud, or ejection from another system. What some ask is whether a distant, slow-moving object, a hypothetical Planet 9, or a passing star a few million years back, could have nudged multiple Oort cloud objects into the inner system at once. That requires a very specific geometry and timing. No published models show it for this particular batch. It remains an open question whether deep sky surveys will eventually find a pattern in comet showers. For now, coincidence is the boring correct answer. Here's the visibility problem. The Atlas candidate is now on the far side of the Sun from Earth's perspective and will remain in solar conjunction for the next 11 days. Ground-based telescopes can't see it. The glare is total. SOHO and stereo can track it for another 2 days as it climbs out of the inner coronagraph field of view. After that, Solar Orbiter, which is trailing Earth in its orbit and has a different sightline, can potentially image it with the MET coronagraph if the brightness holds. Parker Solar Probe has no imaging instruments. What that means is we get a data gap. The Webb observation was a narrow window, grabbed just before the Sun swallowed the view. Any changes in activity, further fragmentation, or tail structure over the next week and a half will be invisible unless the spacecraft catch something. On April 22nd, the object emerges into the morning sky for Southern Hemisphere observers, low in the east before dawn. If it's still intact and hasn't faded, that's when we get our next good look. For those of you who want to see the confirmed comets, here's your guide. C/2025 R2 Swan is your best naked eye target right now. Look west about 45 minutes after sunset. It's sitting roughly 10 degrees above the horizon, slightly north of where the sun went down. Magnitude 4.1 means it will look like a faint star with a fuzzy patch. Binoculars will show a short tail angling up and to the left. The comet is moving north each night, climbing slowly higher, so conditions improve through late April. C/2025 K1 Atlas reaches perihelion on the 16th. Right now it's magnitude 8.8, too faint for the naked eye but easy in binoculars. It's low in the southeast before dawn for Northern Hemisphere observers, about 15 degrees up at morning twilight. After perihelion, it may brighten to magnitude 6 or 7. Forecasts are uncertain because we don't have a Barney-long activity history for this particular comet. 240p, NEAT will top out around magnitude 9, strictly a binocular or small telescope object. Visible in the evening sky near the constellation border of Aries and Taurus in the 3rd week of April. The Atlas Interstellar candidate is the wildcard. If it survives perihelion without total disintegration, and if the outgassing rate holds, models predict magnitude 5 to 6 when it reappears on April 22nd. That would make it a decent binocular comet, low in the eastern morning sky for observers south of the equator, Australia, South Africa, Southern South America. Northern Hemisphere observers will have a tough time. The geometry keeps it low. By early May, it fades as it races away from the sun. The window is short. If you're going to chase it, the last week of April is your shot. Now let's ground this. What's solid? Webb detected a carbon monoxide to water ratio of 8:1 and elevated methane in the Atlas candidate. That's published instrument data, and it's unusual. The object's orbit is currently hyperbolic with small uncertainty. Multiple independent observatories contributed astrometry, and JPL's solution is robust within the stated error. SOHO recorded a brightness spike post-perihelion. The image timestamps and photometry are confirmed. 4 objects passed perihelion in 16 days. That's a fact you can check against the Minor Planet Center's database. What's likely? The object formed in a very cold environment, possibly interstellar, possibly the deep Oort cloud. Another week of trading will resolve the eccentricity question. The brightness spike was fragmentation or a volatile outburst, not an exotic interaction. The clustering is coincidence. These are the boring, scientifically sound conclusions, and they're probably right. What would count as a breakthrough? If the final orbit is confirmed hyperbolic with eccentricity above 1.03 outside, all error bars and the chemistry stays weird, we have our third interstellar object, and the first one we caught early enough to study in detail. If follow-up spectroscopy from ground-based observatories after April 22nd finds molecules that don't exist in solar system comets, we're talking about truly alien ice. If any of the upcoming comets interact with a coronal mass ejection and spacecraft measure both the comet and the solar wind simultaneously, we get physics we can't replicate in a lab. Those are the scenarios worth watching for. Here's what to watch next. The Minor Planet Center will publish updated orbital elements as more observatories submit astrometry through the end of April. JPL typically updates their solution every few days. The web data will go fully public in the Mikulski archive within a week, and independent teams will run their own analysis. If there's anything odd in the spectra that the first pass missed, it'll surface fast. Ground-based observatories in Chile, South Africa, and Australia are coordinating a campaign to image the Atlas candidate the moment it clears the sun. If it's still active, spectroscopy starts immediately. The Keck Observatory and the Very Large Telescope both have directors' discretionary time allocated. We'll know the chemistry story by the first week of May, so that's where we stand. A comet or interstellar visitor with chemistry that doesn't quite fit, an orbit that might be hyperbolic, a brightness spike nobody predicted, and a bunch of other comets arriving at the same time for no apparent reason. None of it breaks physics. All of it is fascinating. The next 2 weeks will decide whether this is a footnote or a headline in the textbooks. Subscribe and turn on notifications because the data will drop fast and we'll break it down the moment it's public.